Hi, geometry students. Last unit of the year. This is unit 14. We're on day 1, and we're still working with circles. This is another unit all about circles. We're going to learn some new things about them. So we're going to start today with diameter perpendicular to a chord and tangents from the same point. So I'm going to go through the theory behind why this works, and then we will get into the problems, which hopefully you'll find to be pretty easy. All right, so the first situation we have in a circle, congruent angles have congruent chords. So in other words, if I say that angle 1 is congruent to angle 2, how can you prove that chords A, B, and C, D are congruent? So I don't know they're congruent right now. I want to prove it. Well, hopefully you noticed that the chords I'm marking right now are all, actually I shouldn't call them chords, the radii I'm marking right now are all congruent because they are radii. So I have side, angle, side congruency. So side, angle, side congruency. So since I proved these triangles are congruent by corresponding parts of congruent triangles, I proved that the chords are congruent. So AB is congruent to segment CD. All right, in a circle, congruent central arcs have congruent chords. So now we're saying that if I know that AB, that arc, is congruent to arc CD, we want to prove that we have the chords congruent as well. So this is almost the same thing as above. Since we have the arcs are congruent, we know that angle 1 and angle 2 must be congruent, and then we know that all these radii are congruent. So again, by side angle side congruency, we have congruent triangles, therefore proving once again that AB, that chord, is congruent to chord CD. So we have that again. A diameter perpendicular to a chord bisects the chord and therefore its arcs. So we're going to do the same thing again with congruent triangles. All right, so let's go ahead and figure out how we're going to come up with these congruent triangles. So one thing you might notice is that you can draw in the radii. Oops, I had to pause for a second, and I don't know what happened to my arrow. There it goes. Okay. So I can connect from O to B and from A to O, and those are radii. So I'm going to mark those as being congruent. And I already have the perpendicular giving me the right angles, and I have this reflexive right here. So do you see this triangle right here, AO, and then I don't have a label right here, and then I have BO and no label right there. So those triangles are congruent. So I know those triangles are congruent, and that is by hypotenuse leg, right? Because I have the right angle. So hypotenuse leg is congruent to hypotenuse leg. All right, so how does that help me? Well, if those triangles are congruent, then that means that I figure out that these two sides of the congruent triangles are congruent. Therefore, I'm showing that it's being bisected. And then how do I know that this arc right here, I'm going to mark in blue, how do I know that these are congruent? Well, if I have these congruent triangles and I know this angle is congruent to this angle, they are central angles, and therefore these arcs are congruent. So all by triangles, I'm able to prove all that. Okay, next. This is something that you should know already about distances, but the distance that a chord is from the center of the circle is the length of the perpendicular segment from the center to the chord. And that's just reminding us, anytime we talk about distance, it has to be a distance that's perpendicular. So I'm looking over at this picture down here, And the distance from the center of the circle that I'm doing right now in blue, that distance to AB, chord AB, has to be perpendicular. I couldn't draw this line right here, and say that's the distance. Nope, that would just be another segment. Anytime I use the word distance, it has to be perpendicular. Okay, so I want to know if two chords in a circle are equidistant from the center of the circle, then they are congruent. Why is this true? All right, so we have these perpendicular distances, and notice they're congruent. So I have the right angle. What happens if I draw in this blue segment and this blue segment? And then I'm going to do on the other side another one and another one. Well, all those I just drew in are radii. That means they're all congruent. So all four of these triangles, 1, 2, 3, 4, are congruent by hypotenuse leg. The radii are the hypotenuse, and then the leg is going to be this right here that I'm marking in red. I'm going to draw it like that. And then they each have a right angle. So all four of those triangles are congruent. Therefore, I'm going to mark in yellow, these are congruent to each other. And therefore, if I add them together by segment addition, I have AB is congruent to DC, right? If this is getting tricky for you to follow, just be sure to know that it's going to get a little better when we throw in the numbers. This is just the theory behind it. All right, so let's go ahead and jump into some problems. So we have given circle A, AF equals AG. So that if they're equal, that means they're congruent. So we have AF is congruent to AG. And we know that BC is 22. Well, if BC is 22, this whole side right here, they want me to find DE. This is the theorem we just went over. Since these are congruent and they're perpendicular to the chords, then we know that this side must be 22 as well. So DE is 22. Next, in the figure, circle P has a radius of 10. In AB, that segment is perpendicular to DE. All right, so we have a radius of 10. So that means this is 10 right here. And we have AB is 8. Well, if DE is perpendicular to AB, then it's going to bisect it. And if AB is 8, then that means this is 4. My pen is not working. I'm trying to write a 4. It's not happening. There we go. 4 and 4. So what's AC? AC is 4. Next, we have DE is 2. So this is 2. And they want to know what AB is. Well, remember, I have a radius of 10. That means that from D to P, it's supposed to be 10. Well, if DC is 2, then CP is 8. So if I go ahead and draw a right triangle in here, right, because these are perpendicular from the given. If I'm going to put the 8 on the outside, if this is 8. If this side is 8, I know what BP is. That's the radius, so that's 10. I just have to figure out what CB is by using the Pythagorean theorem. Or maybe you recognize this as a 3, 4, 5 triangle and already know it. But if you don't recognize it, we're going to say a squared plus 8 squared equals 10 squared. So a squared plus 64 equals 100. So a squared equals 25, or excuse me, 36. Take the square root, a is 6. Remember, it would be plus or minus, but because we're talking about distances and lengths, it's going to be positive. So I have 6. So that's only from C to B. I need the whole segment. So that means 6 and 6, so it is 12. Okay, next. We have in circle G, we have EF is 12 and find AC. So EF is 12, so this is 12 right here. And we're looking to find AC. We're looking to find all of this right here, that whole segment. All right, because these are equidistant, DF and AC are equidistant, then that means that FD is being bisected, so this is also 12. That means the whole thing is 24 and they are congruent, so AC is also 24. Next, we have circle B. We have AB is 10, that's the radius. AC is 16. Find DE. Well, one thing I know is that AC is 16, and because it's perpendicular to the chord, BE and AC are perpendicular, I know that AC is being bisected. So these are each 8. Notice I have a blank 8, 10 right triangle. We just did this problem. This leg must be 6. I can use Pythagorean theorem, or I can just remember it from the previous problem. And now the question wanted DE, that's this piece right here. Well, the radius is 10. Remember they gave it to me up here? So that means that DE must be 4. I don't know what is going on with my pen, but it is not working. So we'll use my finger, 4. DE is 4. All right, moving on. All right, next we have in circle O, AB is 30. So this is all 30. And OM is 20, obviously not drawn to scale. And ON is 18. What is CN? So I'm looking for this piece in yellow right here. Okay, so notice I don't have the luxury of NO and ON being congruent. So I don't know that CD is the same as AB like I did in the other problems. But what I do know is that I can draw in radii like this, and those have to be congruent. That I don't have a choice about. So now, since this is still perpendicular, I know it bisects this. This is 15. So now I can use Pythagorean theorem to figure out BO. So if you're not sure why I'm doing that, you're going to see in a second. So A squared plus B squared equals C squared. So I'm going to solve this. So 6 25, when I add the two of them together, equals C squared. So C is 25. So if this is 25, then so is this hypotenuse. So now I can do another set of Pythagorean theorems to find Cn. So 18 squared plus, I don't know that leg squared equals 25 squared. And now I can solve from there. So I have 324 plus b squared equals 625. Take away 324, so b squared equals 300, or excuse me, 301. And it doesn't say to round, so I'm just gonna take the square root and say that Cn equals radical 301. So Cn equals 301. All right. A tangent to a circle and a radius of a circle drawn to a point of tangency are perpendicular. Why? There's a couple ways to look at this. One way would be to see that if I have this radius that I can turn to a diameter, splits the circle in half. So this arc right here is 180 degrees, and this arc is 180 degrees on the other side. So that means this angle is intercepting this arc, so it's half of it. It's an inscribed angle, special form. So that's 90, and this one's 90 as well. And then segments with a common endpoint that are tangent to a circle are congruent. Why does this have to be true? Well, one way to draw this out is to first draw in a reflexive side that two triangles are going to share. So here it is. And then from the point of tangency, draw to the center. So these are both radii, so they are congruent. And now we already showed that this must be a right angle and this must be a right angle from the previous slide. So by hypotenuse leg, I have proven that these two triangles are congruent, ABO and CBO. So therefore, since they are congruent, I can say that corresponding parts of congruent triangles are congruent. And then how many common tangents do two circles have? It's just kind of a neat thought to think about. In other words, how many different ways can I take a segment and make it so it's tangent to two circles? So play around with this, but you should come up with 4 ways. So here's one. Another one would be going like this. Oops, it's a little tricky doing this not on the board. But that looks pretty good. And then you can have 2 other ways, and that is going from this one down. That one's not the best, but you can see what I'm trying to do. And then here's the other one. So 4 ways you can draw tangents in common with the 2 circles. All right, to the algebra. Find the value of x. Well, what do you know? You have 2 tangents with a common point. That means that 3x plus 7 must equal 7x minus 9. So go ahead and do the computation. Subtract 3x. 7 equals 4x minus 9. Oh my goodness, that pen. Add 9 to both sides, so 16 equals 4x. Divide by 4, and x is 4. Next, we have AE is 15, and EC is 19. They want me to find AC. Okay, so what do I know? AF and AB are both tangent. That means this is also 6. EC is 19. So this whole thing is 19. And I also know that AE is 15. Well, if AE is 15, then this must be 9. These are tangents. So EF is congruent to ED. Since EC is 19, this must be 10, which makes BC also 10, since C is a common point of these 2 tangents. So these are congruent as well. So the question was, what's AC? AC goes from the 6 and the 10, so it's 16. All right. That was a little painful with my pen. I apologize. I'm not quite sure what was going on. But feel free to go back. And I just wanted to point out, a lot of the beginning stuff is all the theory of how we came across all this. So if you're stuck on any of the homework problems, go back to like this one right here, number 1, or 2, or 3, 5, and then I have more of the theory stuff. But focus on the problems if you're stuck, and then you can see how we came about doing those. All right? Okay, if you need anything, please see me in Google Meet for those live video chats, and take care, everyone.